Okay. We will solve this problem on plain electromagnetic waves. Here's what the problem reads. A monochromatic, linearly polarized electromagnetic wave with wavelength equals to 632.8 nanometers is propagating in the negative x direction in vacuum. At t equals 0 and x equals 5.0 times 10 minus 7 meters, the electric field vector is given by, we have the expression for the electric field vector. The irradiance or intensity of the wave is given 100 watts per meter squared. So there's a bunch of questions here. First, what's the electric field amplitude? What's the propagation vector of the wave? Show that this is a transverse wave. Write down the expression for the electric field as a function of space and time, and the magnetic field at the end. So I will start by part C. That's the easiest one. Let's show that this is a transverse wave. The only information we have about the wave is electric field direction, propagation direction. What we know from transverse waves are that if a wave is transverse, the propagation direction and the wave oscillation direction, in this case, for electromagnetic waves, we talk about electric field and magnetic field directions. They're all perpendicular to each other. So electric field vector, magnetic field vector, and the propagation vector. So they need to be perpendicular, electric field and magnetic field perpendicular to the propagation vector. Propagation vector given in the negative x direction. Electric field vector at any point here is given in the mixture of y and z directions, j hat and k hat. So I think the only thing we can do here is show that E is perpendicular to k. So since this is a negative x, we can say, for example, 0.6 j hat plus 0.8 k hat dot product with negative I hat should be 0. It is indeed 0 because there is no I hat here. So that means it is transverse. All right, so that's completed. Now let's go back to part B. What's the propagation vector of the wave? Now, in order to understand the propagation vector, let's first write the full expression for the plane wave solution of an electromagnetic wave. Okay, so the electric field can be written as E naught cosine k dot r minus omega t plus the phase. Okay, phase constant. And here, this k is the propagation vector. Okay, omega is angular frequency. Okay, and p here is the phase constant. So propagation vector is given by its magnitude 2 pi over lambda, and its direction in this particular problem is given to us minus I hat. So that means what we need to do is just plug 632.8 nanometers here for the wavelength, and we're done. That's the propagation vector. Okay. Now let's go back to part A. So we're done with C and B. What's the electric field amplitude? Now, here, electric field amplitude is expressed by this E0 multiplying the cosine term. Its direction tells me about the polarization state. So electric field direction is associated with the polarization state. E0, the magnitude of this vector is the amplitude. How can we find the amplitude from the information given in the problem? Okay. Now, the critical information for the magnitude is irradiance or intensity. Okay. Now, if you study the energy transferred by an electromagnetic wave, you come across what's known as the Poynting vector, and its time average gives me the intensity of the wave. So how much energy per time per area that is transferred. So how much power per area the beam, the wave has. So the relationship for that is intensity is given by 1/2 epsilon permittivity of the material, V speed of the electromagnetic wave in the material times E0 squared. Okay, so this is permittivity. This is speed of the wave. And E0 is the amplitude. So since the problem gives us 100 watts per meter squared as the intensity of the wave, the only unknown here is E0. So now it's given that the wave travels in vacuum, so we're going to use epsilon naught here. If it was in another medium like glass, water, we could use the appropriate permittivity constant for that medium. Same thing with the speed of the wave, vacuum. So it is speed of light in vacuum, which is c, 3 times 10 to the 8 meters per second. Okay, so then in that case, we can write E0 is 2I over epsilon naught c, and I need to take the square root. That's going to give me E0. You plug in the values for what we have here, 2 times 100, everything is in SI units. Epsilon naught is 8.85 10 to the minus 12 in SI units, times 3 times 10 to the 8 meters per second for the speed of light in vacuum. And if you calculate this, I believe you're going to get 274 volts per meter. That's your electric field amplitude. Okay, so we took care of 3 parts. Now comes part D. Write down the full expression for the electric field as a function of space and time. What that means is whatever coefficients we have, whatever parameters we have in this expression, E0, K, omega, phi, we should know them. We took care of E0, magnitude we just found in part C. The direction is given by this expression here. Okay, so the wave is oscillating somewhere between y-axis and z-axis. So that's the unit vector describing the direction of the oscillation of the electric field vector. So that we will take as the direction or polarization direction in this case. It's linearly polarized, that's given. K, propagation vector, we found already. Omega is angular frequency, so we need to determine angular frequency. This is part B. Now, angular frequency is 2 pi times frequency, or 2 pi over period. Okay. So what is the frequency? Well, we know the relationship lambda times the frequency, or lambda over the period, gives me the speed of the wave. This is what's known as the wave phase speed of the wave. Okay, it's monochromatic, so that's what we have, only phase speed. Now, lambda is known, speed of the wave in vacuum is c, so that means frequency will be C over lambda. So let's plug it in. 3 times 10 to the 8 meters per second over 632.8 times 10 to the negative 9 meters. That's the wavelength of the wave. So we can calculate the frequency of the wave. We calculate that, we're going to get 4.74 times 10 to the 14 hertz. That would be my frequency. If you multiply this by 2 pi, we're going to get the angular frequency. So 2 pi times 4.74 10 to the 14 hertz. Okay. So that's going to give me 2 times 2 times 92.98 times 10 to the 15, and then we write the units of this as radians per second, because this brings 2 pi radians. Okay, that's angular frequency. So now we have the angular frequency. What else do we need? We have the angular frequency, we have the propagation vector, we have the angular frequency. This phase constant is what we need. Okay. Now, we need to determine that phase constant. And what information can we use from the problem? You look at it, gives us at time equals 0 and position x position 5 times 10 to the negative 7 meters, the electric field is given to us. So we need to use this information. Okay. So let me copy it over. At time equals 0 and position x position is 5.0 10 to the minus 7 meter. Electric field is given by 0.6 j hat plus 0.8 k hat times 10 to the 2 volts per meter. So I can also write this as, now, this is the direction I'm assuming, okay? So I'm gonna just copy that over because I don't have anything else to assume. That's unit vector, so its magnitude is 1. E0 here, right? E0 is 274 volts per meter. That's what I have for E0. Now this multiplied by cosine of, I have k dot r. Okay, now what is r? R is the position vector. Okay, so I need to multiply that out. So k dot r. And then I have omega t. And then I have phi. Okay, so I know these. So what is k? K is 2 pi over 632.8 nanometers in the minus I hat direction, dot position vector is always x I hat plus y j hat plus z k hat, the vector that tells me the position of the point I'm interested in. So if you do the dot product, obviously there is no j and k that will contribute, j hat a, k hat, because this is I hat dot I hat is 1, the others will not contribute. So this is going to be, this is k dot r. K dot R will be, this is what I'm trying to write as an expression, minus 2 pi over 632.8 nanometers times X. That's what I have. Okay, so this is what I'm gonna substitute here. For omega t, I already know. Now, this is given at t equals 0. So I need to substitute t equals 0 here. So this term will not be important. And this one is at this position. So I'm going to just plug that in here for x. Okay. So this is nanometers. This is in nanometers. So this can be also written in nanometers. So it's like 500 nanometers, so that I can just do the division here very easily. Nanometers will cancel out. I just have radians. Okay. So that means at x equals 500 nanometers, my k dot r term becomes minus 2 pi 500 over 632.8. Okay. And that will give me so what I will get at x equals 500 nanometers is 500 divided by 632.8 multiplied by minus 2 pi minus 4.97 radians. Okay, so that's what's going to replace here. Now, since the vectors are the same on both sides, I don't have to worry. There's only 100 here, 274 here. So let me write it cleanly on the next page. All right. What I have is 100 equals to 274 cosine of minus 4.97 radians plus phi. Okay. So if I divide both sides by 274, then take the inverse cosine, what I'm getting here is minus 4.97 radians plus phi is inverse cosine of 100 divided by 274. So if I can get the angle in radians for inverse cosine of this, then I can determine what phi should be. And when we do that, we get this as 1.20 radians. So phi becomes 1.20 plus 4.97, 6.17 radians. So that means now I found out every single term in my expression. Okay. So I can now write my full electric field expression. 274 volts per meter, 0.6 J hat plus 0.8 K hat. And then I have cosine of 2 pi over 632.8 nanometers times X with a minus sign when we multiply K dot R minus omega. Let's remember what we found for omega, 2.98 10 to the 15, 2.98 10 to the 15 times T. This is in radians per second. And then finally, my phase is 6.17 radians. Okay, so this is the full electric field expression. I have the direction, which gives me the polarization information, amplitude, propagation vector appears here, tells me that it travels in the negative x direction. This is negative, that is clearly in the negative x direction. You can think of this as if time advances to keep the same phase, what should happen here? Okay, so since both of them have negative signs, you're basically adding this to this. So if time goes higher, this should go lower to keep the same phase. In describing the phase velocity, we are basically watching the same phase propagating in the medium. Okay, and 6.17 radians is the phase constant. The last part of the problem is the magnetic field. Now, for the magnetic field, it's in sync with the electric field, but I need to determine the magnitude of the magnetic field, the amplitude, I'm sorry, of the magnetic field and its direction. Part E, magnetic field. So one thing we know about the magnetic field amplitude is its electric field amplitude divided by the wave speed. In this case, because it's in vacuum, we have this 274 volts per meter and 3 times 10 to the 8 meters per second for the speed of light in vacuum. So we'll do this division. That's going to give me magnetic field in Tesla. As long as I keep all these in SI units, I'm going to get the magnetic field in Tesla. All right, let's do that. That gives us 9.13 times 10 to the negative 7 Tesla. That's the amplitude. Now, how about the direction? Well, that this is a transverse wave. If this is the K direction, this is the electric field direction, this is the magnetic field direction. You see the unit vector in the electric field direction cross product with, if we use the right-hand rule, magnetic field should give me K hat. So in these cases, this is what I do. Electric field unit vector, let's say this is the magnetic field vector, unit vector, and then this is the K hat, the propagation direction. So this cross this will give me K. So that means K cross E should give me B. So B direction should be propagation vector, unit vector direction, cross with electric field vector, unit vector direction. So B unit vector direction, propagation vector, unit vector direction is negative I hat. We know that's given. It's propagating in the negative X direction. Cross electric field unit vector direction from the electric field expression. That's also given to us. 0.6 J hat plus 0.8 K hat. There's a little confusion here. This K is the propagation vector, refers to propagation vector. And this one is the unit vector in the Z direction. So 0.6 J hat plus 0.8 K hat. So when we do this cross product, we're going to get magnetic field direction. So for I hat, J hat, K hat, again, I hat cross J hat gives me K hat cross I hat gives me J hat cross K hat gives me I hat. So in this case, I have I hat cross J hat, which gives me K hat. And then I also have I hat cross K hat when I distribute this. I hat cross K hat is in the other direction, so it's going to give me negative J hat. Okay, so if we do that, I hat cross J hat is K hat, so minus 0.6 K hat. And I hat cross K hat is negative J hat. There's another negative here, so it's going to be positive 0.8 J hat. Okay, so that's the magnetic field direction. So if we put it all together, then magnetic field, magnitude, and direction. So we can write magnetic field expression as 9.13 times 10 to the negative 7 Tesla, 0.8 J hat minus 0.6 K hat. That would be its direction. And then the rest is exactly the same as what we saw in the electric field. So it's same K dot R minus omega T plus phi, and it's exactly the same way. So K dot R will be minus 2 pi over 630.8 nanometers times X. Omega T would be minus 2.98 times 10 to the 15 T. This is in radians per second. And then the phi is, again, 6.17 radians. So nothing changes there. So this is the only information we need to change for the magnetic field. So that ends my solution.